We are asked to find the area of the Lune. So the Lune is going to be this area right on over here that's formed by the intersection of these two circles. So now let's just take a look at how this is formed. If we take a look at the smaller circle, we notice that its edge right here where the radius touches the edge of the smaller circle, it intersects the bigger circle's edge perpendicularly. Or it intersects it such that the radius is perpendicular to this imaginary dotted line if we were to draw one down the center of this circle. So this gives us a very important triangle. So if we let this small radius be little r and this big radius be big R, then we also know that this radius over here is going to be big R, and this distance right over here is going to be, let me use, we'll use the same color. So it's going to be the square root of r squared minus little r squared. So this gives us a sense of how long certain things are in this circle. So now, if we want to find the area of this Lune, one way that we could do it is by subtracting areas. So we could first find the area of this semicircle. So if we were to first find the area of the semicircle, and then subtract the area of this, this red section that I'm filling in right now, then we would be able to find the area of this blue Lune. So let's do that. I'll just write down the area of the semicircle, and I'll just draw it like this, is going to be equal to pi r squared, little r squared, divided by 2, because it's half the area of a circle. Now, the area of this red part is going to be a little more tricky. So now let's imagine if we have some coordinate axes. So I'm just going to draw these coordinate axes in a different color. We'll use this brown. So if this is going to be the x-axis, and if this is going to be the y-axis, then what we have here is a circle. And right now we'll consider the positive side of this circle. We'll have this function be y equals the square root of big R squared minus x squared. So this is the function of this semicircle, or more precisely, the top half of this semicircle, right over here. Now I'm going to delete these lines. So what we want now is the area under the curve from negative r, which is here, to positive r, which is here. But one way of doing this is noticing that both sides are symmetrical. So what we can do is have the area of this little red region here. I'll just draw a flatter circle there. The area of that region is going to be the integral from 0 to r times 2, because it's symmetrical. So we don't have to take it from negative r to r. We can just multiply it by 2 and go from 0 to r. And what are we going to integrate? Well, if we integrate this function, root r squared minus x squared, what we are going to get is the area underneath this curve. So it's going to be this entire area, including this box right on over here, including this box. But we don't want the area of this box. So we are going to subtract this. So we're going to subtract the area of that box. And to do that, we have our function. So we have the integral of r squared minus x squared. So that's the entire area. And we want to subtract the area of the box. So that's just equal to the height. So here we have the height, which is root r squared minus little r squared. And this entire thing is taken with respect to x. Now notice that this root r squared minus little r squared, well, that's just a constant. So I'll write that down over here. This is just a constant. So when you integrate a constant, well, you just get the area underneath a line. So we are just going to get the area of this rectangle over here when we integrate this constant. So this integral over here is going to give us the exact area of this little slice that's highlighted in magenta above. So it's going to give us the area of this slice over here. So let's go on ahead and compute this. So we can break this up into two integrals. So let's start by having this. Let's do 2, the integral from 0 to r, square root of r squared minus x squared dx, minus 2 times the integral from 0 to r of root r squared minus little r squared dx. So right now, let's take the easier integral. So right now, we are going to do this integral here on the right-hand side, including this negative 2. So if we were to do this integral, well, it's just the integral of a constant, and what we will get is negative 2, the constant, so r squared minus r squared times x, evaluated at r and 0. So what this is going to give us is negative 2 r square root of r squared minus little r squared. Because if you plug in 0, then it's going to give you a value of 0. So if you subtract 0 from it, it's not really going to do anything. So this is going to be our second integral over here. Now, let's try to compute the first integral. So, what does this first integral tell us? Well, we can use a trigonometric substitution for this. So, if we factor out and the r, if we factor out the r squared out of the square root, well, what would that give us? Well, let me just rewrite this and give it a color so that we can see exactly what we are doing. If we give this a nice orange color, we can move this over here. So this is equal to, or this left-hand side is going to be equal to 2 times the integral from 0 to r. And if we factor out this r, then what we're going to get is r root 1 minus, and this is 1 over r squared. So we have x squared over r squared dx. So now we can do a trigonometric substitution. So this x squared over r squared can also be written as x over r all squared. So we have x over r all squared. So this sort of looks like 1 minus sine squared theta, or 1 minus cosine squared theta. So let's do that. So let's let sine theta equal x over r. Then if we solve for x, then what we'll get is x is going to equal r sine theta. So now if we differentiate both sides, then we'll get r cosine theta d theta is going to be equal to dx. So now we can replace all of the x terms here with r sine theta, and we can replace dx with r cosine theta d theta. So let's just continue on over here, and I am going to rewrite this. So we have 2, the integral from 0 to r of r times the square root of 1 minus, and since x over r is going to be sine theta, so we have sine squared theta. And since dx is this term over here, we're just going to write that down. So r cosine theta d theta. And if we keep going, maybe we'll go on to a new page so that we can actually see what we are doing. We will have, I'm just going to start at the top again, 2 times the integral from 0 to r. Now, this r is actually now in terms of x. So right now, it's supposed to be in terms of theta. So you know what? What I'm going to do is I'm just going to cross this out, and we'll pretend like it never existed. And we're just going to rewrite our integral in terms of x later on, and we'll just keep it as an indefinite integral for now. So we're going to have it be 2 times r squared. 1 minus sine squared theta is cosine squared theta. So this is going to be cosine theta times cosine theta d theta. So right now we can also rewrite this as 2 times r squared, the integral of cosine squared theta d theta. So now from our trigonometric identities, we know that cosine squared theta is equal to 1/2 1 plus cosine 2 theta. And this can be proved by the double angle formula. So now that we know that this is the case, well, if we plug this into our cosine squared theta over here, then the 2's here cancel out. And what we are left with is this expression being equal to r squared times the integral of 1 plus cosine 2 theta d theta. So if we continue, we have r squared, and we can take the antiderivative of 1, which gives us theta, the antiderivative of cosine 2 theta, which gives us 1/2 sine 2 theta. And right now, since we're taking the definite integral afterwards, we can just ignore the plus c for now. So right now, sine 2 theta can also be written as 2 times sine theta cosine theta. So using this identity, we can rewrite 1/2 sine 2 theta as sine theta cosine theta. And now we can plug in our original theta. So let's try to remember what our original theta was. So we set our original theta to be, let us see, okay, so sine theta is equal to x over r. So let's write that down over here. So we know that sine theta equals x over r. So what we have here is a triangle. Let's draw it. So if this is our angle theta, then sine theta is x over r. And by the Pythagorean theorem, this adjacent side is going to be r squared minus x squared. So theta, we can really just write that as arc sine of x over r. So let's just write that over here. R squared times arc sine of x over r. And now we're going to add sine theta, cosine theta. So sine theta is x over r, and cosine theta is root r squared minus x squared over r. So right now we want to evaluate it at r and 0, because that is what we wanted to do with our definite integral. But before it was in terms of theta, but now it's back in terms of x. So now we can evaluate. So let's just plug in our values. So we have r squared arc sine of r over big R. So let me just write what we are evaluating at. So we want to evaluate our integral at little r to 0. That's what we established in the previous slide. So we're going to plug in our r's now. So arc sine of little r over big R plus, so now notice how this r squared can cancel out with both of these r squares. So I can just close this parentheses, and now these r squares all cancel out. So this x is going to be a little r, and here we have the square root of big R squared minus little r squared. So this is what we get when we do the definite integral from 0 to little r. So right now what we're going to do is we are going to put everything together. So I am going to create a new page over here. So going back to our very first page, what we can see is that the area of the Loon, so now I'm going to write it here, area of the Loon is going to be equal to the area of the semicircle minus the area of this thin strip. Okay, so we will just right now write that on our blank slide. So A Loon equals A semicircle minus A slab thingy. So we know that the area of a semicircle is 1/2 pi r squared. Now, what is the area of that slab thing? Well, if we go back to our first slide, then what we can see is the area of the slab thing is equal to this orange part plus this yellow part. So let's find what the orange part is equal to. Well, we solve for the orange part right over here. So it is equal to r squared times arc sine of little r over big R plus r times the square root of r squared minus little r squared. So let's write that down over here. So we have, so the r squared, so I'll just put it in brackets, r squared, arc sine of little r over big R plus r square root of big R squared minus little r squared. So this is the first part, and this is the red part, or the orange part that we were looking at earlier. So now let's take a look at the yellow part. So what is the yellow part? Well, the yellow part is negative 2r root r squared minus little r squared. So let's write that down. Here we have still in the parentheses minus 2r root r squared minus little r squared. So now, if we distribute the negative sign in, we can actually first simplify this because we have minus 2r root plus r root. So they can just be minus 1r root. So let me just write that. So we have 1/2 pi r squared minus r squared arc sine r over big R. And here we have minus 1 r root big R squared minus little r squared. So then we have plus 1 r root big R squared minus little r squared. And this is the equation for the area of the Lune.